Alright, now let's talk about refraction. This is the one that's going to make your head spin a little bit, because there's a lot going on here. We're going to deal with lenses, and lenses are a lot more complicated than mirrors. There's a lot more scenarios that can happen. There's only two types of lenses, convex and concave. But what happens with the convex lens is pretty complicated, so there's a lot more scenarios to deal with. This is also where the math is going to come into this. We'll be calculating indexes of refraction, and we'll be calculating some angles. So this is where the math will come in as well. So it's going to be a bit more complicated than what the reflection part was. Refraction is the bending of a wave as it passes into a medium with different density. So the wave is cruising along through the air, and then it hits something with a different density like water. And it passes into the water this time. It doesn't bounce off of it. The wave goes into the water. Or it's a light wave cruising along through the air, and then it comes to a window and it has to move into the glass. Air and glass have different densities. That's going to affect that wave as it moves into the glass. And what it's going to do is change its velocity. It's either going to speed the wave up or slow the wave down depending upon the density of the media and what kind of wave it is. Light waves behave differently than sound waves. Light will slow down as it enters a higher density medium. So as air to glass happens, as the light is moving through the air and then hits the glass, it is moving into a higher density media, and it will slow down. These are the speed of light in different media, in different substances with different densities. You can see here it's at its highest in a vacuum, because light will go fastest in a low density medium. Air has a slightly higher density than what a vacuum does, so you see it slows down a little bit. If we round this one, it's 2.998. This one is 2.997 times 10 to the 8th. So it slows down a little bit as it moves from a vacuum into air. As it moves into water, it slows down more from 2.997 to 2.26 times 10 to the 8th. As it goes into glass, it would slow down even more, from 2.26 times 10 to the 8th to 1.97 times 10 to the 8th. And as it moved into an even higher density media, like diamond, it would slow down even further, going less than half the speed that it does in a vacuum. So again, there's this kind of misconception that the speed of light is constant. The speed of light is constant as long as the medium is the same. So the speed of light in a vacuum is always 2.9979248 times 10 to the 8th meters per second. But as you go from one medium to another, it will speed up or slow down. So as we go from air into water, as we go into a higher density medium, it would slow down. If we went from glass into water, it would speed up. So the speed of light does change dependent on the density of the medium it's moving through. Basically, the particles in that medium affect its motion. It scatters it, reflects it, bounces it around some, and keeps it from moving as fast as it can. Sound changes in the opposite way. Sound increases in speed as it travels into higher density media. Sound is a mechanical wave. Sound needs matter to travel. And the more dense that matter is, the faster it can travel. It's a compressional or longitudinal wave. This particle has to pass energy onto this particle, which has to pass energy onto this particle, which has to pass energy onto this particle, and so on. The more dense it is, the quicker that can happen. The quicker that energy can be passed on from one particle to the next. So the more dense the medium gets, the faster the speed of sound will be. In air, at 0 degrees Celsius, the freezing point is 331 meters per second. In warmer air, it will be faster because the particles are already moving faster. So we'll go from 331 meters per second to 343 meters per second. Not a tremendously big increase, but there is an increase with temperature. Sound will travel faster in hot air than it will in cold air, and again, it's because of particle motion. We have to pass energy on from one particle to the next. In warm air, the particles are already moving faster, so that process happens faster. This is where the big jump happens though. As you go from air, where it's in the mid 300 meters per second, into water, it jumps all the way up to 1,482 meters per second. So it's a very large increase, almost 5 times faster in water than it is in air. Then if we jump it up into some very high density, high elasticity materials like glass and steel, again, almost a 5-fold increase from about 1,500 to almost 6,000 in steel meters per second. Ever seen old Western movies when the train robbers are trying to find out if the train's coming down the track? They'd put their ear to the railroad rails, the steel rails, to hear if the train is coming. That's because the speed of sound is much faster in the steel rails, so it will get there quicker, and it will also travel further in the steel rails than it will through the air. So light slows down as it enters a medium with a higher density. Sound will actually speed up as it enters a medium with a higher density. Here's our illustration for refraction. And again, just like reflection, I would expect you to be able to interpret these. I'd expect you to be able to draw these. Our straight line this time that our incident ray is going to encounter is the barrier between the two different media. We have air on the top, we have water on the bottom. The surface of the water is my barrier in this case. Again, incident ray is still the ray that is approaching that barrier. Now, like I said before, this is actually a wave front. It's a series of crests and troughs, or a series of compressions and refractions. It's a wave front that's moving in. And we are just picking a point on that wave front and tracking it as it moves along. This is the path that point will take. That wave will travel in a straight line. So the incident ray is the one that is approaching the barrier. The refracted ray is the one on the other side. And again, this is just a wave front moving along, and we're picking a point on that front and we're following it through. This is the path that point would take. Again, traveling in a straight line, because that's what light does. So incident ray, that's the wave that is approaching my barrier. The refracted ray is the wave on the opposite side of it, once it's passed through that barrier. We have a normal again, and just like before, the normal is that imaginary line drawn perpendicular to the surface at the point of incidence. And point of incidence is not labeled on here, but it's right there. That's where the incident ray strikes that barrier. Again, perpendicular, so it's a 90-degree angle. This time it's drawn all the way through the barrier because the wave is going to pass through the barrier. Once again, we have angle of incidence. Angle of incidence is, again, the angle between the incident ray and the normal, just like it is for reflection. So this angle here is my angle of incidence. This time, we have an angle of refraction instead of angle of reflection, because it's moving through the barrier. But just like before, it's measured between the refracted ray and the normal. All your angles are measured against the normal, not against the surface, not against the barrier. All of your angles are measured against the normal. So this is the angle of incidence, this is the angle of refraction. This time those angles will not be equal. Refraction is going to cause a change in direction of our wave. It's going to cause our wave either to move in this direction away from the normal, or move in this direction towards the normal. And what it does depends on how that velocity is going to change. If the wave is slowing down, as light would do when it enters a higher density medium, if the wave is slowing down, that wave will be bent towards the normal. It will be bent that direction, towards the normal. And what will happen is your angle of incidence, this angle here, will be greater than your angle of refraction. You will reduce that angle as light moves from a lower density medium like air into a higher density medium like glass. Anytime the wave slows down as it moves from one medium to another, it will be bent towards the normal. And your angle of incidence will be greater than your angle of refraction. If the wave is going to speed up, you'll have the opposite effect. As the light goes from glass into air, from the high density medium into the low density medium, it's going to speed up. and that will cause it to be bent or moved away from the normal. So in this case, the angle of incidence is less than the angle of refraction. The angle of incidence is this one, the incident ray and the normal. The angle of refraction is this one between the refracted ray and the normal. The angle of incidence is less than the angle of refraction. So in reflection, they're equal. The angle of incidence equals the angle of reflection. In refraction, they're not equal. The only way they could be equal is if these two media had the exact same density. What you're going to see is a situation where either the angle of incidence is greater than the angle of refraction, and that happens when the wave slows down or light moves from a low-density medium to a high-density medium, or you'll have a situation where the angle of incidence is less than the angle of refraction, and again, you get that when the waves speed up. You go from the high-density medium to the low-density medium. You think about the way that a window works. It starts with light moving from air into glass. So it's actually going to slow down and be bent towards the normal. Then it's got to go from the glass back into the air again, where it will be bent a second time. And that will cause the wave to move back away from the normal again. This is why when you look through glass and you look through air, you'll see a slight shift in the image on the other side. Never done with glasses. You look through the glasses, look over the glasses, look through the glasses, look over the glasses. You'll see the object appear to shift slightly. That's because of all this refraction that's taking place. Alright, I'm going to end this video here because that's enough. That's just basic refraction stuff. Now we're going to get into the math in the next video.